Everyone can hear me, right? Can someone respond to like in the chat box or something? Let's wait for a couple of minutes more as people are joining in.
आम्ही जेवणच नाही केलं. मी थोडी हे माय कॉल नाही ना.
Yeah, so let's start with the basics of this thing. I'm not sure if I'm visible enough or not. Okay, so yeah. So welcome to this session. There is a problem-solving session for the course Sensors and Actuators, which is an 12-week course. And my name is Shomnath Bhattacharjee. I am a PhD research scholar in the Department of Electrical Engineering, IIT Jodhpur. So I'll be conducting this like 12-week like problem-solving sessions and everything. And so, so this is the basic about me. As I've already told that I am pursuing my PhD in the Department of Electrical Engineering, and my research interests are towards flexible and organic transistors for neuromorphic computing, and which are very in line with this course, as like I needed to like do some kind of fabrication and like fabrication of sensors and those kind of a things. And so like I have completed my bachelor's in physics, and after that I've completed my master's in electronics. So the for this course the class schedule will be on every Sunday from 6 to 8, and we'll meet on every Sunday, and we might also have a extra class based on based on the like instructions I get. So I guess I'll conduct 12 or 13 like sessions like this. So moving on to the course content. So the course is basically lay out in 12 different course structures or course structures. So the from the very start we'll learn about the basics of energy transformation, transducer, what is sensors, actuators, and those kind of things. Afterwards, we'll learn how to fabricate these sensors. So in this one, in the first one, we'll learn about the basics of these transducers, what are sensors, and these kind of a things. In the next one, we'll learn about what are, sorry, just a second. Yeah. Yeah. So on the next one, we'll learn about how to fabricate these sensors and actuators, what are the techniques used to fabricate these sensors, and also in which environment, or like let's say if we are fabricating these things in a clean room or something, what are the protocols to follow and these things. In the next section, or the third class, we'll learn about what are the recent trends, what are the research domains in this sector, and how these clean room equipments are being used, and how to maintain this protocol over while using this equipments, and also while fabricating the sensors as well. So in many of the steps we don't need to use any kind of a specific equipment, but we'll need to maintain these protocols when we are working inside a clean room and everything. Yeah. So on the fourth one, we'll learn about the basics of this fabricated sensors, and we'll go through again about this entire fabrication procedure and how these sensors are interfaced with an interfacing circuit for various real-time applications and these kind of a things. Further, we'll learn about some of the materials like silicon as a substrate. So, silicon can be used as a substrate. We know that the conventional electronics, most of the conventional electronics are based on this silicon or silicon derived oxides or some things like that. So, like silicon, silicon dioxide, and these things. Then we'll learn a bit about not that much deep. We'll not dive deeper into COMSOL all these kind of a things, but we'll learn how to use the COMSOL multiphysics tool or these kind of a things to like realize fabricated sensor. Then we'll learn more about the a specific example, that is a gas sensor demonstration for VOCs and these kind of a things. Then we'll learn about the photolithography and different interfacing circuits like the signal conditioning circuits, sensor interfacing circuits, and these kind of a things for a specific case, that is for a temperature sensor. Then we'll further move on to PVD techniques and different equipments being used for these kind of a things. Then further that we'll learn about the one of the most important fabrication like procedures, that is the photolithography. And we'll learn more about some specific alloys that are known as the shape memory alloys, which retain their shape based on the memory element stored in it. Then further, we'll move on to cancer diagnosis test and Arduino-based applications. So we are moving towards on the like last half of this lectures. We'll move on to more exemplar way, and we'll move on to these kind of a things like cancer diagnostics tests and like Arduino-based applications of these kind of a things. Then we'll move on to the mechanical phenotyping of a tissue for a biochip, like specific kind of a say we can say we are moving towards a e-skin type of a thing, that where we are fabricating a skin that is not that is not physical, that is an electronic one, but it will have all kinds of applications and all kinds of property that a normal skin have. Then the penultimate lecture will be on flexible MEMS. Why do we need a flexible platform or flexible substrate for these sensors? And like it can be conformable, it can stick onto your hand, and these kind of a things. Why do we need these things to be flexible? And then further, we'll move on to the CAD modeling of these biochips, the fabricated biochips. And finally, we'll move on to the future aspects of this course, or let's say this domain specifically, sensors and actuator fabrication towards flexible, towards biomedical things like cancer diagnosis and Arduino based applications like IoT applications, and even like edge computing applications and these kind of a things, and towards realization of these sensors through 3D printing and these kind of a things. So this is the basic course structure, and the course throughout these lectures, what I'll do is that I'll start with the basics of basics of the lectures, what you guys have already gone through throughout this week, and I'll just brief about them, and then I'll move on to few questions, and then we will discuss that why how to solve that numerical problems or how to solve that theoretical problems, and what is the basis of that solving and these kind of a things. And these problems will be very similar to what you will encounter in each week's quizzes. So it will be helpful for you guys as well. So let's move on to the first part of this course, that is the week 1, that is basics of energy transformation. So we'll learn the basics of transducers, sensors, and actuators. Then we'll move on to the physical properties. So what physical properties are used in the sensors or actuators, and how we are trying to utilize these physical properties in realizing this kind of a sensors. And further, at the last part of this lecture, we'll know about what kind of materials can be used to fabricate these sensors and so forth. So let's move on to the basics of these things. So basically, what is a sensor and what is a transducer? So in a simple word, we can say that a sensor is a device that measures a specific parameter let's sorry. Yeah. So a sensor is a device that measures a specific parameter. So it in most of the cases it is a physical parameter. Is it visible? Yeah. So it is a physical parameter and it converts into a signal. So it is converted into a signal. So it is converting into a signal, and this signal should be readable. So it should be in a readable format as well. So a device that measures a specific physical parameter and converts it into a signal or a readable format. Let me write it down, readable format. Okay. So in other words, also we can say that a sensor acquires a physical parameter. Let me write it down. Physical parameter into what? Into a signal, but that is like processable signal or a readable format. Now, so what is a transducer? Transducer is a device that converts one form of energy to another. So sensor also does the same, right? So sensor is converting a physical parameter. Sensor is converting a physical parameter into a processable signal. Let's say in English, let's say in electrical signal or something like that. So from a physical parameter to an electrical signal. So one form of energy to another. So that's why we can say that transducer is like sensor is a type of a transducer as well. So a basic transducer is like this. So it contains two of these halves. So the first half is sensor. So what does the sensor do? Sensor takes this measuring quantity that is a physical parameter or something like that, and it converts into a processable signal. Then what happens is that this processable signal goes from this side to this side through an signal conditioning circuit. So this is a signal conditioning circuit. Conditioning signal conditioning circuit, and this signal conditioning circuit does what? These signal conditioning circuits take the readable or processable signal and converts it to an useful info. So if you are getting, let's say, if you have a sensor and it converts and like, let's say, sound to an electrical signal, you won't be able to hear that, right? So you need a signal conditioning circuit to convert it into a readable or useful info. So if you hear a sound, you know how high pitched it is or something like that. So you need a signal conditioning circuit or a center interfacing circuit to convert it into an useful info. So that is a complete transducer, and a transducer has two parts, so like sensor and a signal conditioning circuit. Now, so if we are moving on to different kind of examples, a microphone or a mic, what does a mic do? Can any one of you like explain to me what does a mic do in a basic sentence? You can say. You can turn on your mic and let me know, or you can write it down in the chat box as well. Yeah, sound signal into electrical. But how does it like does that? So ideally, what it does is like it converts acoustic energy to electrical signal, right? Any basic idea how does it like converts this acoustic energy to an electrical signal?
There is some diaphragm and which will vibrate over the voice signal or sound signal, and then maybe there is piezoelectric kind of material, so it will generate a signal.
Then what about a speaker?
Speaker have also similar kind of setup, but here we convert the electrical signal to some mechanical
No,
vibration, so
that's
it
fine.
will.
Electrical to an acoustic signal, we are converting it, so that's perfectly fine. But how does a speaker work? So if we are vibrating the diaphragm with an electrical signal and it vibrates, and based on that vibration, we hear the sound. So this is
Right.
this is the one of the most basic or layman term to just explain this. But just like explain this one then. So based on that exact theory, like explain the working of a speaker. What are the major differences between these two? Because we can see the diaphragm in a speaker, right? It's very
Right.
visible to us, but we can't
Right.
see the diaphragm in this microphone. Yeah, speaker converts electrical to acoustic, right? So I was just writing that.
In a speaker, there is a coil which vibrate due to EMF, electromagnetic force,
Hmm. Perfect, perfect. That's perfect.
and
But
by this, yeah,
my question is that we can see the diaphragm in the speaker, right? It's clearly
right,
visible to us, like even with like small kind of like speakers to an larger ones. So like
yeah. Once we screw the upper part, there is a diaphragm. We can
yeah,
visit.
so it's clearly visible, but not in a mic. Why? So even like I'm using AirPods, right? So it has a mic in it.
Right.
Otherwise,
In mic, that is inside one. I think there is some kind of a steel packaging or aluminum packaging.
hmm.
So, yeah, we not means never I have tried to break that one also.
That's fine. That's fine. I'm just asking.
So,
So, is there a thing that like while we are converting an acoustic energy to an electrical energy, we need a smaller diaphragm, and for converting electrical to an acoustic one, we need a bigger one or something like that?
maybe I'm not sure.
Okay. Anyone? It's an amplifier. It increases the amplitude of the electrical signal. Yeah, kinda right. Any other explanation of this? So, what's the basic difference between a microphone's working, and a speaker's working? I'm just asking that. So we know that it converts the acoustic energy to an electrical energy, and speaker converts electrical energy to an acoustic one. So they are just clearly opposite of each other.
Sir,
Yeah.
my view is a microphone converts mechanical to electrical, no doubt, but the transducer is different. They use some piezo transducer, which are sensitive to mechanical vibrations in the air and converts to electrical pulse. Whereas in the speaker, that input is an electrical signal, and that signal moves some coil diaphragm,
Hmm.
which creates waves and audio.
Yes. That is the
So both
correct
are
answer. Yeah.
transducers, but they're different kind. It is not one. It is not exactly reverse of the microphone, but it's a different kind of transducer. That's all.
Yeah. Correct. Correct. This is the correct answer. So they don't have the actual they don't have the similar kind of a working principle for both of these. So like there are several different kinds of microphones as well, and there are several different kinds of speakers as well. So there are in-ear speakers, and there are several different kinds of speakers as well. But the basic one works with the basic thing, that is you are using your voice, and it is getting converted through a piezoelectric sensor to an electrical signal. And in case of speakers, we need a diaphragm. A basic airflow is needed to create the sound. So if you are creating a sound, so you need a much bigger area diaphragm and everything. So you need to convert the electrical signal, that is like coming from the like device itself, and it will convert it to a sound signal or an acoustic signal based on the movement of the diaphragm. So there's a basic difference between these two things, but you need to learn need to know that in case of sensor, the signal needs to be readable format. So that's the one of the most important things in this case. So let's move on to the next one. So that is how to choose these sensors. So based on different kind of phenomena, we can divide these sensors in different classes. Based on device architecture, we can divide these sensors in a different different parts and everything. So let's start with the physics. So based on the basic physics, we can divide the sensors in multiple branches. So it can be thermal, it can be mechanical, it can be optical, it can be electrical, like this. So there are different kind of phenomena. So if you're converting in thermal energy to an if you're converting in thermal energy to an electrical signal, let's say, so it will be an temperature sensor or a thermal sensor. And if you're converting an mechanical force or a pressure or something like that, then it will be a mechanical sensor. So based on these kind of things, there can be electrical signals, optical signals, and there are several things. Similarly, yeah. I'll share the PDFs and everything. So like you will, I guess within a couple of days, you guys will have this. Yeah. So based on the physics involved, these are different kind of a sensors. Similarly, based on the device architecture, so there can be several device architectures. So based on the field effect transistors, so there are transistor-based thermal sensors, transistor-based pressure sensors, and these kind of a things. Based on NEMS, nano electromechanical sensors, based on MEMS. So most probably in the lectures, you guys have already learned about the MEMS, that micro electromechanical sensors, which told in NPTEL course. Yeah, sure. So based on the size of this electromechanical sensors, so these are in a nanometer range, and these are in the micrometer range. So these are based on the device architecture itself. Now, based on the several different kinds of applications. So if you are using it to measure a physical quantity, let's say if I am giving pressure to a certain thing, and that is a physical quantity, right? So if I am measuring what kind of a pressure or what kind of a force I am putting on a certain thing, then it's a physical sensor. Similarly, if we are measuring any chemical quantity, it is a chemical sensor. And if we are measuring any kind of a environmental parameter, like let's say in agricultural fields, we need to know when there is a dew or something like that. So that will be an environmental sensor. So based on the applications, we can also divide these sensors in a various different things based on the substrate use or the foundational layer use. So what is a substrate? Substrate is a foundation layer on top of which you are on top of which you are fabricating the sensor itself. So this is our substrate, right? So if we are let's say we are making a tabletop sensor or some kind of a thing, so we can anyways use rigid substrates like, let's say, glass substrates or silicon substrates, the conventional substrates, I would say. And like for let's say why we need to use a glass, right? So in case of LEDs, if we are making these kind of a things that uses the optical input to any kind of a sensor, so we need a glass because it's transparent and it will not it will not block the optical ray or LED or some kind of a light or those kind of a things. Similarly, in kind of a conformable sensor, let's say we need a sweat patch. So you need to stick it on top of your hand or wrist or something like that, right? So you need a flexible one. So flexible can be different kind of a thing. So it can be PET, PI, these kind of things. So PET is like we know that PET bottles are there, right? So for any kind of cold beverages, we use PET or polyethylene terephthalate. Similarly, there are PIs, PVC, there are PVC pipes. So there are these kind of a flexible substrates can be also used based on the application itself. So moreover, application and substrates are kind of related, but although based on the substrate use, we can fabricate these sensors on a flexible foundation or also on a rigid foundation as well. Similarly, as I have already told, that based on the dimension, there are nano. If these are in a nanometer range, so they are called NEMs, and similarly, if they are in a micrometer range, they are called MEMS, and those kind of things. Now, based on the active materials, so in specific use cases, you need to use several different like materials to fabricate these devices. So let's say if you are using a something, yeah, yes, you can ask me. Yeah, yeah. Do you have any question? You can ask me. Do you have any question? I guess not. Okay. Sure. So, based on the active materials, so what are these active materials? So, we know that in conventional electronics, silicon is the one of the main active materials, and also germanium. And then there are recent ones that are 3, 5 components like gallium arsenide and these kind of a things. But in newer domains or recent times, researchers are conducting research on different kind of a polymers. They can be organic polymers and these kind of a things. And why they are using it? Because in need of a biocompatible structure. So what is a biocompatible structure? So let's say if I am using a specific sensor outside of a human body, so we don't need to change any kind of material. We need the stability and we need the long time usage and these kind of a things. But if let's say we are using a sensor inside our body and we need to plant it, so if we are using a silicon sensor or a germanium sensor over time inside our body or something, it will harm our body. It is not a biocompatible one. So what is a biocompatible? Biocompatible sensor or biocompatible electronics is something that it is compatible to a biological cell. So if you need a sensor that is in a very close proximity to an biological cell or something like that, or let's say organs or these kind of a things, so you need it to be a biocompatible sensor. So biocompatible. Similarly, if there's another field, so like in case of biocompatible, there can be something called the edible sensors. So let's say if you have a sensor, you need to eat it, and after not digesting it, after swallowing it, so it will go inside your body. It will give you data for let's say 2, 3, 4 hours, and after that it will dissolve inside your body. So these kind of sensors are edible sensors. In these kind of things, you won't be very happy if the sensor is made out of silicon or germanium, right? So you need something that is non-toxic to your body, and after its intended lifespan, it will degrade inside your body itself. So these kind of things are like can be possible with using polymer, and based on this polymer, we can enable these kind of applications like biocompatible, edible, biodegradable, and these kind of things. Similarly, based on the state of the sensor, so if we are measuring let's say some kind of a liquid, and so it can be in a liquid state, but for a very solid analyte and these kind of things, we need to use like we can use a liquid state or a solid state. So similarly, based on the sample that is we are trying to measure the quantity from, and based on what we are intending to achieve, there can be a liquid state sensor or a solid state sensor. There are gaseous state sensors as well, but they are not as common as these two things. Similarly, based on the measurement techniques, so there can be direct and indirect sensors. So direct sensors are something that if let's say a piezo sensor, so if I am giving force to it, it will measure the electrical response to against my pressure, the given force or given pressure, right? So it is a direct direct change in the material, and based on that, we are getting the direct answer. There are several indirect sensors. So let's say there are several different kinds. I'm not going into details of this, but there are several different kinds of thermal sensors that with the change of resistance we measure the change in temperature. So based on that, we can say it is indirectly mentioning the change in temperature, but we are calculating it, so we are not getting the measurement directly, so it is called an indirect sensor. So apart from these kind of a things, so let's say that let's also discuss about this. So based on different phenomena, so like based on detectable phenomena, so we can have different kind of sensors. So as it is very relevant to our course, we need to know these kind of things. So the first one being optical sensors. So optical sensors can be of different types, right? But it have like several different key parameters we which we need to utilize to like sense this like sense the changes or sense the physical parameters, something like that. So in case of optical sensors, refractive index can be a good way to measure any kind of a changes or something. Similarly, absorption of something. So your blood flow or these kind of a things, or even like blood oximeter and these kind of a things, they use the optical sensing parameters and these kind of thing. And similarly, there can be of thermal sensors. So thermal sensor is very straightforward. It uses temperature, specific heat. Another very common one is mechanical sensors. So mechanical sensors use obviously pressure, force, velocity, acceleration, and also position. There are acoustic sensors, as we have already mentioned, like mic and speakers. So acoustic sensors, what they do is that based on the wave property, we can utilize these kind of a sensors. So based on the wave property, so based on the wave property is like the phase of the wave, or even the amplitude of the wave. What is the amplitude of my voice and these kind of a things we can be utilized to make the sensor. Apart from that, the velocity of the acoustics is also important. So there can be apart from this, obviously there can be electrical. So electrical sensors, the most common ones are the currents and the voltages, resistivity. Any kind of a resistance based sensor is the electrical resistivity sensor. Conductivity. There are chemical sensors as well. So these works on basis of the concentration of the concentration of the analyte we are using to the concentration of the chemical we are using to do this, and also rho, that is the density of the let me write it down, I guess. Density of the chemical being used. So there are several other kinds of sensors as well, like let's say magnetic sensors, which measure the magnetic flux and these kind of a things. So there are several different kind of a sensors. So the main aim of this slide was to let you know that there are several different kind of sensors, and based on different parameters. So like if we are considering the physics involved, it we can say there are several different kind of sensors like the thermal, mechanical, optical, electrical, these kind of a things. Similarly, based on the use case, that is the based on the substrate use, so it can be a flexible sensor or it can be a rigid sensor. So as I have already told you guys, so we'll learn about the flexible sensors as well in the penultimate week of this course, and different kinds of states, so like liquid state and solid state. So if we are measuring any kind of a liquid thing, so we'll use the liquid state sensors. Now we'll move on to the materials. So there can be several different materials. So like there are plethora of materials in these sensor fabrication. So the first important thing is the substrate. So this one is a substrate. You can see, I guess. So this is a substrate. This one. So what does a substrate do? Substrate is only the foundational layer of any kind of a sensors. So it doesn't have any kind of a function at all. It just provides the basic foundation needed to fabricate the sensor on top of it. So these kind of substrates can be rigid like silicon, glass, and these kind of things. Similarly, flexible like PI, PVC, PDMS, PET. So these kind of substrates can be used. So as it is not foundation, not functional, so we are not going in deep into these kind of materials. Similarly, on top of that, this is a basic heater. So I'll describe the basic fabrication procedure of this heater, but let us learn about the functional layers first. So on top of the substrate, there is a electrode, metal electrode you can see. So this electrode material or like these electrode materials can be made out of different things. So it needs to be conductive. That's it. So any kind of a conducting material can be made electrode. So what kind of materials can be electrode? So most of the cases we use metals like gold, silver, platinum. These are one of the best kind of metals we have, and they have the most highest conductivity. So there is no drop in between these lines. So here you can see, I guess there are several lines and these kind of things. So there should be no drop between these two contacts. So that's why we use a very highly conductive material like gold, silver, and these kind of things. Similarly, there are several conducting materials as well, like different polymers. So polymers can also be conducting. P.PSS, it is an organic polymer, and PCHT, it is also another polymer. These are conducting polymers, and these can be used as an electrode as well. Although we know that like depositing a gold, silver, or platinum, these kind of metals are very easy, and like we have been using them for centuries. So like they are easy to deposit and they are very easy to utilize in a fabrication step or something. But utilizing a P.PSS or PCHT is not so straightforward. Similarly, there are several different conducting oxides as well, like ITO, indium tin oxide. This is indium tin oxide, and this is FTO. So these kind of materials can be also used for in place of metal. So if we are using for a biocompatible one, we know that gold is biocompatible, that it doesn't harm our body. So many of us like always wear a gold ring or silver ring or platinum ring. So that's why these are already biocompatible. But if we are intended for a specific use case, let's say um, we have a any kind of a optical sensor, and we need the sensor, the basic of the sensor. So let's say only we need the sensing material here. The sensing material needs to be it doesn't need to be transparent, but the conducting material or the conducting electrode needs to be transparent, and also the substrate needs to be transparent. So what will you choose in that case? Out of these substrates and electrodes, can anyone answer this question? So if we are intended for a transparent one, so we intended to use a transparent transparent sensor, among which only the sensing material doesn't need to be transparent. So out of these materials, what will we choose to fabricate this sensor?
Polymers, sir, conducting polymers, transparent.
No, they are not like in general, polymers are not transparent. So like let's say P3ST. P3ST has a very reddish tone, and P.PSS is bluish. So the most use case for these kind of oxides like ITO and FTO, they are completely transparent. So in recent research and everything, sorry, recent recent research and everything, so people, if we are required to use transparent oxide, we need to use ITO or FTO. Yeah, someone has answered something. Yeah, substrate needs to be glass. Perfect. So we can see that glass. So now there is another problem as well. So glass have a very high transparency, right? So it is the transparency of this is something nearly like this. So glass doesn't block any kind of a light through it. Similarly, if we need it to be flexible, PET is also an important option because it is 99.3. So it is obviously blocking a bit of light, but if your sensor doesn't need to be 100%, so you can use PET or something like this. So these are transparent substrates as well. So if you are moving towards a transparent sensor, You can use glass if you don't need a flexible one. If you are intending for a flexible one, you can use PET. PI is also transparent. Similarly, PDMS can also be made transparent and also non-transparent as well. Similarly, if we are moving towards an electrode like ITO, FTO, these are completely transparent. Now, moving towards the one of the most important like functional layers. So these are the sensing materials. So what is the sensing material? This part is the sensing material. So based on the phenomena of the sensing material, the total phenomena of the sensor like is dependent on this material itself. So different kind of sensing material is used for different kind of a sensors. Let's say if you are fabricating an organic transistor or a conventional transistor. So an organic transistor based or an conventional transistor based sensor, it can be of anything. Let's say humidity sensor. So if you are fabricating a humidity sensor with organic transistor or a conventional transistor, so there can be two different kinds of a sensing layer as well. So we need a semiconductor. So semiconductors can be different types of things. So it can be a polymer. So for the organic transistor, we need a polymer. And similarly for let me use that one. Wait. Yeah. So for the organic transistor, we need a polymer semiconductor. Similarly, for an conventional transistor, we need to use an conventional semiconductor like silicon or these kind of a things. Now, there can be several inorganic semiconductors as well for these specific use cases. Like if you need a transparent one, as I was saying, so IZO, that is indium zinc oxide, or IgZO, that is indium gallium zinc oxide, these kind of a materials. This is also an oxide, right? So this is also a transparent one. So if you need a completely transparent device, you can use IZO with PET or with glass and with tin oxide and FTO. So everything will be transparent. So your total sensor, so if you are holding this sensor, let's say like this, and it will be completely transparent as well. So similarly, if we need an insulator, so for these transistor-based sensors and these things, you need an insulator, right? So it can be any kind of a polymers like PVC, PVP, PV, and these kind of a things. Similarly, there can be inorganics like SiO2. Recently, hafnium has also gained certain attention. There can be TiO2, Al2O3. So there can be different kinds of oxides of different inorganic materials can be there, and also there can be these are polymers. So PVC, PVP, PVA, these are different kinds of polymers. And if you need a specific kind of a conductor, so there can be different polymers. So these kind of polymers can be P dot PH, P3ST as well, and there can be different carbon-based like conductors as well. And why we are like have like we are exploring these many materials because of different use cases. So if you are moving towards a transparent one, you need different materials, different conductor, different semiconductor, different insulator, different substrate, different electrode, and these kind of a things. If you are intending for a different use case, so you need different kinds of materials. And for each kind of application, you need to know that there are several different materials that can be better than what you are using currently right now. Now let's move on to this one, the sensor fabrication. So this is a very basic heater fabrication. So what is this? This is a substrate. So in this case, they have chosen a basic substrate here. And on top of the substrate, there is an electrode. So they have patterned this electrode like this. I'm talking about this second one. So they have patterned this electrode in an interdigitated pattern, IDE, or inter electrode ID pattern or interdigital electrode pattern. So they have patterned this thing. Now the patterning is through photolithography. What we'll learn it after I guess on week 4 or week 5. And so when we reach there, I'll talk more about this photolithography and how this patterning happens. But let's say if we are depositing this material in a certain way, and on top of that there is this sensing material. Let me change the color first. So let's say this sensing material is on top of everything. So this is your sensor area. Okay, so based on that, this is the sensing region, and these are your contacts. These are your contacts for measuring the electrical parameters. So based on the sensing, so if let's say there's a change in heat, and based on that we can sense the parameter change into these two contacts. So the basic pattern looks like this. This is a complete heater. So there can be a complete heater like this. Similarly, there can be a complete thermal sensor like this. So, and here you can see this is the heater pattern, right? So if we are heating this sample, we'll get to know the change in the this sensing material, and based on that change, we can have the values from this contact regions as well. So this is a very brief explanation of an fabrication technique, and we'll learn more about this. So how do we control the environment and in the clean room, and what are the protocols to follow in a clean room? How do we use different kind of equipments? What are these equipments, and what are they helpful for? So there can be different kinds of patterning techniques. There can be different kinds of deposition techniques as well. So there are PVD, CVD, and these kind of things. So CVD is a chemical vapor deposition, and PVD is a physical vapor deposition. So based on different deposition techniques, and there are several advantages and also disadvantage of each of these techniques. There are several advantage and disadvantage of each of these materials, and based on your application, you need to choose which application, which material is best for you, which equipment is best for your use case, and everything needs to be optimized. So a sensor fabrication is not a very straightforward way, but you have to choose that. Let's say like I need a transparent sensor. You might not like, let's say it is very unnecessary for a thermal sensor to be transparent, right? But you need to fabricate a transparent sensor. There can be a separate use case for you. So you need transparent materials. Let's say these transparent materials are not very durable under very high temperatures. So you need to set the limit of this sensors as well. So let's say these materials or a few of functional layers are getting destroyed after, let's say, 150 degrees. So your temperature sensor, if your use case is, let's say, you need to measure up to 130 or 140 degrees centigrade, so you can use this sensor in that case. So in your use case it can be useful. But if I am measuring, let's say, 180 degrees centigrade, so I may not be, it may not be useful for my use case as well. And in my use case, let's say I don't need it to be transparent, so I'll use a different materials and different technique as well. And based on the cost, so one of the most important factor to choose the material. So and also the equipment usage is also the cost as well, because we know that polymers are very cheap as well. And like FTO, ITO, these are very high quality oxide films, so they are not that cheap. And conventional silicon transistors and these kind of things, they are not very suitable for a large area production as well. So if you are using a polymer, it can be very easily be deposited using a spin coating technique or a deposition technique, where you don't need a very huge electrical equipment with that consumes a very huge power. It takes a very long time and something, so you don't need that. So, and also for these kind of a CVD or PVD techniques, you need a very high vacuum as well. So achieving that vacuum also requires a very large energy consumption. So you don't need that as well. So if you are moving towards something, a very low cost thing, you can utilize polymers as well. So based on your use case, you need to choose a specific material, you need to choose a specific equipment to use, and you also need to define what parameters are important for you. So based on, say, let's say there are several sensing parameters. So you can say that my sensor is very accurate. Someone can say my sensor is very precise. And based on your use case, you need to think that if you need a more accurate sensor, if you need a sensor with a huge range, or it is enough to have a very small range, and if you need to be a very precise sensor or something like that, so based on your use case you need to choose the materials, you need to optimize the process flow of this sensor fabrication, and also use utilize a specific equipment which is also in your budget as well. So now we'll move on to the questions for this. So as is the first class, so I'll not take that much time for this. So let's start with a very few simple ones. So a sensor. So before this, so if anyone have any question, you can ask me. So we have gone through some basics of this course and the basics of sensors, transducers, the basics of how to choose a sensor, how to fabricate a sensor, and based on the use case, what materials to choose, what equipment to choose, and these kind of a things. So if you have any questions about these things, you can ask me. Are there any questions? I guess not. So we'll have enough time after the class as well. So if anyone have any question, you can ask me at that time. So a sensor acquires a physical parameter and converts it into a signal suitable for processing. So is it true or false?
True, sir.
Yeah, it's true. So there are three different factors to check. So the first one is that it needs to be a physical parameters that is measurable. So there is no need to right now check the measurable term, but in most of the cases you need to find out that if there is a measurable physical parameter, something like that. So as it converts to a signal that is suitable for processing. So another factor is also fixed. So it is a processable signal or or let's say a definable signal, something like that, suitable for processing and everything. So it is a true. Similarly, let's go on to the next one. So which of the following is best suitable for the quantities below. So we have three different kind of sensors. One is acoustic, second one is magnetic, and third one is optical. Now the quantities they have told us, first one is refractive index. Let's write it as A. B is reflectivity. C is flux. D is I guess, where was D? No, there is no D. So there are three things. Yeah. So what are the answers? Optical, optical. So for which one? Yeah,
Optical is for refractive and
yeah,
reflectivity.
yes. So this one is optical. This one is also optical.
And
And
magnetic is flux.
yes, magnetic flux. Let's move on to the next one. So this was an question. So MEMS is the acronym for what? So these are similar kind of a problems that quiz questions. So you will have to encounter in this course. So this is as this is the basic one. So these are very theoretical ones, but afterwards I'll move towards more mathematical ones and those things. Okay. Yeah, micro electromechanical system. So the first option is micro electromechanical systems. Second one is micro electro materials systems. Third one is micro electric machining systems, and the fourth one is micro electric mechanical systems. So I guess there are few answers, right? So micro electrical mechanical system. Yeah, the first one is correct one. Yeah. Now let's move on to the next one. So now I haven't like described the silicon crystal growth process and everything, but let's do this. So in the silicon bowl growth process, we have to just arrange the steps, right? The first one is crystal pulling. The second one is beginning of crystal growth. Third one is introduction of seed crystals. Fourth one is formation of crystal. And the last one is melting of polysilicon. So just arrange it in a cycle. So what is the first step and what is the like what is the second one, what is the third one?
First is introduction of seed crystal,
Okay,
then
three.
formation and melting of polysilicon. No, no. The last one is I know. The last one is crystal pulling. Yeah.
Yes. So this is 53214. 53214. Someone wrote 53241. 32451. 32451. No, it's wrong. 51324. 51324. 53241. So obviously the first one is melting of polysilicon. So this is the fifth one. What is the next one then? Several people have wrote one and several have wrote three, right? Hmm. The next one is three. That is the introduction of seed crystal. First we melt the polysilicon and then we introduce the seed crystal. And then what for others? 53241 you have wrote 214. So after introducing the seed crystal inside the polysilicon, the crystal growth will be so this will be beginning of crystal growth. So that is number two. The next one will be which one? Number one, right? Crystal will be pulled out. So crystal pulling is second, and the final one is number four. That is formation of crystal. So as soon as you start to pull it out, and there will be formation of crystals from the top to the bottom. So formation of crystal, that is number four. So this is the basic process. That is, we'll start with the melting of polysilicon, then we'll introduce a seed crystal in it. Then when the crystal growth starts, we'll just pull the crystal upwards, and based on that, the total formation of the crystal will be done. So there are several different processes as well, like the Chokral-Jaski process, and they are the different processes as well. So you guys need to learn about that, like for making like silicon crystal, or making a silicon what do I say, like making a silicon film or those kind of a things. So like how silicon dioxide are being made. Just a second. Yeah. So how the silicon dioxide are being made based on the thermal processes, or there are several deposition processes and these kind of a things. And based on that, so there will be these crystal growths, and how we are making these oxide layers and these kind of things. So let's move on to the next one. So the next one is, which is not a PVD technique. So physically depositing a vapor is called a PVD technique, that is physical vapor deposition techniques. So there are several options. The first one is thermal evaporation. The second one is sputtering. Third one is thermal oxidation. And the fourth one is E-beam evaporation. So can you guys explain each of these techniques in a single line or so? So what is thermal evaporation, what is sputtering, what is thermal oxidation, and what is E-beam evaporation? So in the later half of this course, I'll explain with the working principle and everything, but you guys can just like tell me a single line about each of these techniques.
Sir, thermal oxidation is basically a chemical process. So that is one which is art there. Whereas thermal separation is a physical process. Sputtering is also a physical activity.
Yeah. So
E-beam also.
my question is like, what is the main working principle of a thermal evaporation? What happens in a thermal evaporation? So like, just describe it in a single line or so.
Yeah, when you evaporate, then the solid that particles stick to the surface. The gases will evaporate,
Yeah,
and
kind of a right. Yeah.
yes.
Anyone can explain it like in a better way or something? Let me tell you. Yeah. So Pallav, Prince, you have raised your hand. You can answer, right?
Yeah, for sputtering, I can answer. In sputtering, we have a cathode and anode pole,
Hmm.
and then on a means we use a target like which material we have to sputter on a
Yes.
substrate. So
Yes.
we use their target in presence of plasma chamber like argon plasma or something,
Yes.
some kind of the center.
Inside a plasma environment. So all
Yeah,
of these techniques are like, not all, but like most of these techniques are under a plasma environment. So you
okay,
need
right,
a very high vacuum and those things as well. Yeah.
right.
Continue.
So in that sputtering technique is PVD technique,
Hmm.
and
Yes. So
like
sputtering, what happens in a sputtering is that we sputter an specific like material like through a target to an substrate, and it just gets there and stuck on it. So this is a very highly what do I say, like very highly pure layer forms through this sputtering technique and everything. So this is a PVD technique.
Yeah.
So can you explain thermal evaporation or something?
In thermal evaporation, we use material to evaporate, means use a metal to melt and then it evaporate and it will, vapor will stuck to the
Yes, perfect.
substrate.
Yeah, so based on a resistive boat, and we give a very high electrical current to it, and the resistive boat heats, and based on that heat, the metal gets converted into a gas, and that gas is thrown towards the targeted sample, and based on that, they stuck onto the surface of it. So this is basic thermal evaporation. So this is also an PVD technique. Similarly, a very similar thing happens in E-beam evaporation. So in E-beam evaporation, what happens is that we utilize an E-beam instead of thermally heating the material. So we use E-beam to heat it up, and then it gets converted into gas and it gets stuck on the sample itself. Only thermal oxidation is different because with thermal energy we are converting silicon into silicon dioxide, like few parts of the silicon into silicon dioxide. So this is not an PVD technique. So let's move on to the next one then. Now, extracellular and intracellular matrices are responsible for giving, sorry, giving nutrition to the cells. So is it true or false? Based on the bionic chips described in the lectures and these things, false. Why? Can you explain it?
Sir, only extracellular matrix is responsible for giving nutrition to the cells.
Okay. So then what is the work of an intracellular matrix?
It is for supporting the cells, sir. That as a support.
Hmm, not correct. Not entirely correct actually. So any other one?
That intracellular matrix may be the composition of the constituents of that cell.
So which one is the structural, or let's say the basic foundational structural architecture of an which one is the architectural matrix actually? The structural one.
The structural one is intracellular.
Intracellular, sir.
Yes. And then what does the extracellular do? So it takes the nutrient inside the cell itself and it utilizes that. It is not let's say, yes, it is responsible for giving the nutrition, but it is not entirely bringing the nutrition to the cell itself. So I am just asking that. So it is anyways false, so you are correct. But the point is that what do we say, like nutrition is getting to this point at the extracellular matrix, and then it is distributing it, distributing the nutrition. Yeah.
Actually, I not get the question properly. Maybe
Yeah,
that's
so I am saying that extracellular and intercellular matrices both are responsible giving the nutrition to the cell.
okay.
So
No,
are they both responsible for giving the nutrition to the cell or not?
no, intracellular is responsible for giving the cell nutrition.
And which one is the structural one then?
Intracellular.
No, I am asking which one is the structural one and which one is the nutrient, which one distributes this nutrient to the cell itself. So it is obviously false because both are like
Yeah,
both doesn't have the
intracellular.
same work. Yeah, can you repeat it again?
I think
Uh,
someone had a question.
yeah, sir, you state the true sentence, sir. I am also getting confused. You just state the true sentence, then I
Yeah,
think
so
that will be.
the true statement is that extracellular is the structural and the functional layer which holds the cell itself, and intracellular matrices uses or distributes the nutrition inside the cell itself. So in this case, intracellular is the one that does the work, and extracellular is provides the structural and foundational formation of the cell. So this is wrong and this is right, ideally. And because both of them doesn't work in giving the nutrition to the cell, so this is false. The statement is false itself. So the answer was right, but I was saying that which one does contribute to itself, like which one does contribute for which of the cases.
Hello, sir. I'm again confusing.
Yeah.
Suppose if I make the statement, intracellular matrices are responsible for giving nutrition to the cells. Is it correct
Yes.
statement? Okay. Okay, sir.
Yeah, it's correct. But what I am saying is that they distribute the nutrition to the cell. So are responsible for giving nutrition to the cell. It is correct. But does it give nutrition to the cell? No. They are responsible for giving nutrition to the cell because they are distributing the nutrition to the cell. You got it?
No, giving a nutrition or distributing
No, no, no.
nutrition.
Responsible. No, no, no. Focus on the point. Responsible. I'm talking about the responsible. So they are distributing the nutrition to the cell, but they are not bringing the nutrition to the cell itself. That's why they're responsible to giving the nutrition to the cell.
Okay, sir.
Yeah. Now let's move on to the next one. Fill in the blanks means dash means study outside the living body, and dash means study inside the living body. Ex vivo and in vivo, right? So the answer is sorry, I guess you guys can. So this is ex vivo and in vivo. So inside and living body is called in vivo, inside it, and outside outside the living body is called ex vivo. Now let's move on to the next one. So this is also from the lectures itself. So what is the work of CD4 cells? What is another name of CD4 cells? And what is the name of CD8 cells? So there are three options. One is helper, second one is T regulatory, and C is killer. Helper and killer, right?
Sir,
So
CD4 cellular helper and CD8 is killer.
yes, and also to this is also with respect to T cells in the microfluidic chips. Now let's move on to the next one. So for a sensor, which one is the desirable one? So sorry. So for a sensor, which one is the desirable characteristic? So the first one is the specificity of the sensor should be low. Second one is power consumption is low, and SNR or signal to noise ratio is low. Let's remove this and write it as is low. B, and explain why the others are not the correct ones. Like explain your answer. That's it.
Sir, actually, the specificity of sensor should be high. It should be
Yes.
specific to
Hmm.
the measure and what we want to
Yes.
measure.
So we don't need to we don't need a interference from a different analyte or something like that. So if we are measuring, let's say, ammonia, we don't need carbon monoxide or carbon dioxide to be detected by the sensor itself. So the specificity needs to be high.
Yes, sir.
Yeah. The next one.
And it should consume low power.
Yeah.
Okay, the
That's
power consumption
perfectly
should be
fine.
low.
Yeah.
Okay.
That's
And
perfectly fine.
signal to noise ratio, the signal should be high with respect to noise.
Yeah.
Ratio should be high.
Yes, because if there are,
Yes,
let's say, environmental noises and those kind of a things, the signal needs to be high and the noise needs to be low, or the ratio needs to be a much higher one, because we need to only analyze the signal itself and we need to remove the noise from the signal. So that's why it is the correct one. So B is the correct one. And let's move on to the next one. So which among the following sensors are used to detect VOCs or volatile organic compounds, sorry, exhaled from breath? So the options are A, ultrasonic sensors, B, infrared sensors, and C, others. So to measure VOC, yeah, C is the correct one. So what kind of a sensor is needed?
Gas sensor.
Yes, gas sensor is needed. So volatile organic compounds are compounds such as IPA, that is isopropyl alcohol, or ethanol, or acetone. So these are organic compounds that are very volatile, and so to let's say, what do we say, like to detect them, we need a gas sensor like setup, and these can be used for like alcohol sensing, the alcohol in your breath, and these things can be sensed through this. So we'll conclude today's session here, and from the next one, we'll move more deeper into the, just a second, more deeper into the course structure. So this was one of the basic classes, and from next class onwards, we'll move on to the fabrication of the sensors and the techniques and clean room protocols and these things. So that will be also another like basic theoretical class. And afterwards, we'll move on to the these problems and what are the real life challenges with fabricating these sensors and these things. So thank you all for attending the session. And if you have any questions, so you can ask now. Yes.
Can you let me know about some more about the interdigited electrode?
Yeah,
Means,
sure, sure, sure. Yes, do you have any specific question or something? You can ask me.
means this term I have heard in lecture, and that's why I want to know more
Yeah,
about.
so in most of the cases, so what is one of the desirable thing is that, so we have two different electrodes like this. So if we are fabricating, let's say, electrodes like this, So these are your two electrodes. Let me change the color first. So let's say electrode A and electrode B. So these are the region where they are conducting the electronic current. So if we are just, let's say, judging by this, let's say this is a transistor. Let's say based on transistor, I'm just explaining this. So this is a transistor based sensor that can detect humidity or something like that. So you have an effective area of this. So this is your W by L, right? So in transistor, one of the major parameters is its aspect ratio, and that is W by L. So you have a very fixed W by L. So now, how to improve the performance of this transistor? And whose question was this? Something, I guess Pallav, right?
Yeah.
Yeah. So how to increase this transistor's W by L? What are the ways to improve this W by L?
By adding some metal part between this gap,
No,
means
no.
conducting.
So what you can do in this case is that either so either
We can increase the silicon oxide layer.
no, not entirely. So, that is so like by increase the silicon oxide and those things. So you are increasing the C value. So that you are increasing the capacitance value. So we are not going towards that. So we are talking about the W by L. So how to improve this W by L? Either by increasing the width, either increasing the W, or by
Or
reducing L,
somewhere.
right? So let me just remove this. So I am talking about W by L. So either you can increase W or reduce L, right? There are two ways to do this.
Okay.
Now, if we are going towards a, let's say, interdigitated pattern of only two hands, let's say like this, and in this factor, you have something like this. Just ignore my bad drawing, but understand the basic phenomena behind this. So you have a structure like this, and you have a structure like this. So what is the thing that has been changed from the left image to the right one? This space between these two. Okay, there's a space between these two. So these two are same, exact same. So what is
Okay.
the basic difference? Let me explain it. So these factor and these factor. So we have made the L constant, right? We are not changing the value of L. Now what is W? W is this factor from here to here to here to here, from this up to this, right? Sorry. Yeah. So up to this is right now W. So what we have done is that we have increased the W value and we have made the L as constant. So right now your W by L is much higher than the previous W by L. Is it okay?
Yeah.
So what we are doing here is that we are making an interdigitated pattern, and here I am just explaining it with you, you with only two hands, right? So there can be several hands like this, and by this you can increase the W by L with a very much higher factor. So it can be
Okay.
increased with 100 or 200 times as well. And based on the number of so they will be like this, yeah. So based on the number of hands, you can increase the W by L as well. So this is for a transistor, but for a different kind of a sensor, you are increasing the sensing area. My main thought is this. So you previously it was like this, right? Only this one was your sensing area, but right now everything is your sensing area. So you are increasing the sensing area, but you are still limited within a very small fraction of area. The total area is very limited for both of these. There is a little change in between these two structures. So the total area, if you are saying, let's say 1 inch by 1 inch, so this is a very big one, right? But within
Yeah.
1 inch by 1 inch, if you are making a transistor with this left configuration, and if you are making a transistor with right configuration, you will have a very much higher like higher response to any kind of a change in humidity with respect to the right sided transistor, because you have a very huge sensing area itself. So that's the main factor. You are increasing the sensing area.
Okay.
So that's why the different kind of architectures are there. So in some of them, this metals are in the downward side, so they are like, what do I say, like they are protected from the environmental effects. So if you are leaving your sensor, let's say outside for, let's say, 2 years or 3 years, so your sensor won't perform as a new one, right? So even if you are purchasing an electronic device, so if you are using a phone every day, and you are checking the phone's battery life after, let's say, 2 years, it won't be same, right? So there are several different architectures to protect the electrodes. There are several architectures to protect the uh, active sensing layer. So there are several different techniques, and by increasing this like active sensing area, you are increasing the performance of the device itself. So this is a basic thing.
Okay. Okay. Thank you.
Hmm. There was another question, right? So who was it? Another question was there, right? I'll try to, Dipanjan, I'll try to like share the PDF as soon as possible. I guess in the first week it will take a day or two, because I'll send the link to NPTEL and they will share the link with you guys. And afterwards, the other PDFs will be shared in the link itself. So you will find the PDF within a day or something. But the first one, I guess they will take at least a day or two. So thank you everyone. Thank you for attending today's session. So let's meet on the next Sunday, uh, around 6 or something. Yeah. Thank you.